The sinc function. The name sinc is a contraction of the Latin sinus cardinalis, or cardinal sine function. The definition that we will use is sinc of t equals sine of t divided by t. It is sometimes called the unnormalized sinc function. The sinc has its peak at t equals 0 and has decaying oscillations on either side of t equals 0. When we zoom in, it is clear that sinc of t has 0 crossings at integer multiples of pi, except at t equals 0. The formula given for sinc of t yields an indefinite value at t equals 0. However, by L'Hopital's rule, we may evaluate the limit of sinc of 0, as t goes to 0, to be equal to 1. Thus, the sinc function is continuous over all time, has a peak value of 1 at t equals 0, and decays according to 1 divided by the absolute value of t on either side of 0. It may be shown that the area under the curve is pi. Another definition for sinc exists. This essentially is the same function, except compressed in time by factor pi, so that its area is equal to 1. That is why it is called a normalized sinc function, for which I use notation sinc sub n of t. Many others label it as sinc, so one must be aware of the two different definitions. In MATLAB, for example, the built-in sinc function is the normalized version. When using MATLAB's sinc, you can divide the argument by pi to obtain the unnormalized sinc output. As seen in this graph, the normalized sinc sub n of t has its 0 crossings at integer values of t, except at t equals 0. Let's return to the definition of sinc of t that we will use. That is, sinc of t equals sine of t over t. You may be wondering, what's all the fuss about this sinc function anyway? What is it used for? This will become clear later when we study the Fourier transform. But for now, let's just say a rectangular pulse in the time domain is equivalent to a sinc pulse in the frequency domain, and vice versa. These two functions are equally important in our design of filters and in understanding the theory of digital to analog conversion.